Welcome back. In this video, we're going to look at examples of representing functions with power series. Let's get to it. All right, so here's our first example. We want to find a power series for the function f of x is equal to 3 divided by 2 plus x centered at c equals 0, and we want to determine the interval of convergence for that power series. All right, so when we want to find a power series to represent a function, what we want to do is get that function in a form that closely resembles the sum of a geometric series. All right, and so remember that a geometric series is a series of this form where we have the sum from n equals 0 to infinity of a constant a times the common ratio r raised to a power of n. And a geometric series converges when the absolute value of that common ratio is less than 1. And so when the geometric series converges, it will have a sum, and that sum is equal to a divided by 1 minus r. Okay, and so if we want to represent this function as a power series, what we have to do is manipulate it so that it's in the form of the sum of a geometric series. And what that will allow us to do is rewrite that function into a geometric series, or more specifically, a geometric power series, right? Because what we're going to have is some constant divided by 1 minus the common ratio, and that common ratio is going to include the variable x. Okay, remember that for a power series, there's two different forms. If the power series is centered at 0, we just have the sum from n equals 0 to infinity of x to the power of n times some sequence a sub n. Or if the power series is centered at some other value c, then we would have the sum from n equals 0 to infinity of the quantity x minus c to the power of n times some sequence a sub n. All right, and so notice that for both of these power series, we have x, or x minus c, raised to the power of n. And so x and x minus c are going to correspond to the common ratio r, because r is raised to a power of n as well. So we want to rewrite our function in this form of the sum of a geometric series where r is going to include x or x minus c, depending on where we want our power series centered. And that way we will be able to rewrite that expression as a geometric power series. Okay, so if we do that for this function, we're going to be working with f of x is equal to 3 divided by 2 plus x. What we want to do is rewrite this function in this form. We want to have some constant divided by 1 minus r, where in this case r will be equal to x, because we want to find a power series centered at 0. All right, and so currently this function is not in this form. We do have a constant in the numerator, but we're dividing by 2 plus x. We don't have 1 minus x. And so what we have to do is manipulate this denominator. The first thing that we can do is remember that two negatives make a positive, so we can rewrite this function to look like this. This would be equal to 3 divided by 2 minus negative x, right? 2 plus x would be the same as subtracting negative x, because those two negatives will cancel out to be positive. But now we have 2 minus a common ratio. In this case, it's a negative x. All right, it doesn't matter that we have a negative times that x. Having a constant multiple for x is all right. As long as we have that x in the common ratio, we're good to go. All right, so now our function is closer to being in this form. Now what we have to do is change this 2 to be 1. We want to have 1 minus a common ratio with x in it. All right, so what we can do to change this 2 to be a 1 is multiply the function by a form of 1 half divided by itself, right? So what we can do is multiply by 1 half divided by 1 half. You're always allowed to multiply by a form of 1, right? 1 half divided by itself would just be 1. And by doing that, 1 half times 2 will be 1. And so then we'll have 1 minus some common ratio. All right, so if we simplify, this is equal to 3 halves divided by 1 minus negative x divided by 2. All right, so 1 half times 3 is 3 halves. 1 half times 2 is 1. And 1 half times negative x is negative x divided by 2. Okay, and so now our function is in the form of the sum of a geometric series. We have a constant in the numerator divided by 1 minus a common ratio involving x. All right, and so we would say that for this function, that a is equal to 3 halves and r, the common ratio, is equal to negative x divided by 2, right? A is the constant in the numerator, and r is the common ratio that is being subtracted from 1. And so we could rewrite this function to be a geometric series, or more specifically, a geometric power series, by writing it in the form of the sum from n equals 0 to infinity of a times r to the power of n, right? Since we have our function in the form of the sum of a geometric series, we can just rewrite that as the geometric series. So if we replace a and r with what they're equal to, we'll have that our function is equal to the sum from n equals 0 to infinity of a, which is 3 halves, times the common ratio, which is negative x divided by 2 to the power of n. All right, and so now we have our power series that represents this function, but we can simplify it a little bit so that it looks nicer. And so if I clean up my work, what I'm going to do first to simplify this is separate this negative from x divided by 2. Right, what I'm going to have is the sum from n equals 0 to infinity of 3 halves times negative 1 times x divided by 2 to the power of n. All right, so negative 1 times x divided by 2 is the same as negative x divided by 2. But now what we can do is take each of these parts to the power of n. We can take negative 1 to the power of n, x to the power of n, and 2 to the power of n. And so if we do that, this will be equal to the sum from n equals 0 to infinity of 3 halves times negative 1 to the power of n times x to the power of n divided by 2 to the power of n. Okay, and now we can simplify further by noticing that we have 2 and 2 to the power of n in the denominator, which we can multiply together to combine their exponents, right? We have the same base of 2. We have 2 to the first power and 2 to the power of n. If we multiply them together, we'll add the exponents and have 2 to the power of n plus 1. All right, and so this will be equal to the sum from n equals 0 to infinity of 3 times negative 1 to the power of n times x to the power of n divided by 2 to the power of n plus 1. That is the power series centered at 0 that represents this function f of x. All right, so you can clearly see x to the power of n, that is this part right here of the power series, and then the rest of it makes up a sub n, the sequence that's being multiplied by x to the power of n. All right, so this power series represents our function, but now we need to determine the interval of convergence for that power series. And so remember that a geometric series converges when the absolute value of r is less than 1, and so we can apply that same requirement to this geometric power series, right? We can look at this value of r for our power series and take the absolute value of it and see when it will be less than 1. So if I clean up my work, we want to check to see when the absolute value of r is less than 1, and r in this case is negative x divided by 2, so we're going to look at the absolute value of that and see when it's less than 1. We want to solve for the values of x, and so these absolute value bars are going to eliminate this negative sign. So what we're going to have is the absolute value of x divided by 2 is less than 1. All right, and then at this point, the absolute value bars aren't going to affect this 1/2 or this 2 in the denominator, so we can pull that out, and we'll have 1/2 times the absolute value of x is less than 1. Now, if we multiply both sides by 2, that will eliminate this 1/2, and that will give us that the absolute value of x is less than 2. All right, and so now at this point, we can actually determine the radius of convergence. We have the absolute value of x, which is the variable expression from our power series that's raised to the power of n. Since we have the absolute value of that expression and it's less than 2, the radius of convergence will be 2 for this power series. So you can make a note of that if you wanted to. The radius is equal to 2. All right, but now we can find the interval of convergence by remembering that the absolute value of x less than 2 is implying that x is less than 2 but greater than negative 2. That's what the absolute value of x less than 2 is saying. We just removed those absolute value bars and then included that lower endpoint, which is the negative version of the other endpoint. Okay, so when x is between negative 2 and positive 2, our power series is a convergent series. And so the interval of convergence is from -2 to +2. That is our final answer. We have the power series that represents our function, and this power series is centered at 0, and the interval of convergence for that power series is from -2 to 2. In other words, this power series only represents this function for the values of x between -2 and 2. Okay, let's look at another example. All right, so here's our second example. We want to find a power series for this function, f of x is equal to 4 divided by 3x minus 20, centered at c equals 6, and we want to determine the interval of convergence. All right, so this time we're working with the function f of x is equal to 4 divided by 3x minus 20. So if we want to represent this function as a power series, what we need to do is get it in the form of the sum of a geometric series. We need to have some constant divided by 1 minus some common ratio involving x. In this case, that common ratio needs to involve x minus 6. And that's because we want to find a power series centered at c equals 6. Right, so in the general form of a power series, we had x minus c to the power of n. But in this case, we want our power series to be centered at c equals 6, so we need to have x minus 6 somewhere within that common ratio. Okay, so that's what we're working towards as we manipulate this function to be in this form. But what I want you to notice about this function is that in the denominator, we have 3 times x minus 20. And so that 3 is going to affect what that common ratio will look like. Instead of just looking for x minus 6, what we're going to look for instead is 3 times x minus 6. Okay, we need to account for that coefficient of x. All right, so if we multiply 3 through this quantity, then we'll have 3x minus 18. And so 3x minus 18 is what we want to have in our denominator. All right, if we have that in our denominator, that will be part of our common ratio that we will need to have in order to rewrite the function as a power series. Okay, and so how are we going to get 3x minus 18 in this denominator? Well, we already have 3x, but we have minus 20. So what we can do to get negative 18 is split up this negative 20 into two parts. We could have negative 18 minus 2. Right, so we'll say that this is equal to 4 divided by 3x minus 18 minus 2, because negative 18 minus 2 is equal to negative 20. So we split that up, and now what we can do is reorder this denominator, because now we have 3x minus 18. That's what we want to have in the denominator for our common ratio. And so if we put the negative 2 out front, this will be equal to 4 divided by negative 2 plus 3x minus 18. All right, remember that this 3x was positive, so we have plus 3x minus 18. Okay, but now, in order for this to be in the form of the sum of a geometric series, we have to be subtracting that common ratio. But in this case, we are adding 3x minus 18. So what we have to do is change this plus sign to be a negative and negate both of these terms. Right, so this is similar to what we did in the previous example. This will be equal to 4 divided by negative 2 minus negative 3x minus 18. All right, so we negate the two terms that we want in our common ratio, and then we subtract them, and that is the same as adding both those terms, because those two negatives would cancel out to become positive. All right, and so now we're really close to getting our function in the form of this sum of a geometric series. The only thing we're missing is this 1, right? We have negative 2 minus our common ratio, but what we want is 1 minus that common ratio, okay? The numerator is fine. We have a constant of 4. That's going to be a as of now, but that's going to change because what we need to do here is multiply by a form of 1 that is going to change this negative 2 to be positive 1. And we can do that by multiplying by negative 1/2 divided by itself. Right, negative 2 times negative 1/2 will be positive 1. All right, another way you could view this is that we're dividing the numerator and denominator by negative 2. That's the same as multiplying by negative 1/2. And by doing that, we're changing this negative 2 to be positive 1. Okay, so if I clean up my work here, let's go through with this multiplication. 4 times negative 1/2 will be negative 2. So this will be equal to negative 2 divided by negative 1/2 times negative 2 that's 1, and then we're going to be subtracting negative 1/2 times negative 3x minus 18. Those negatives will cancel out, and so we're just going to have 1/2 times 3x minus 18. Okay, and so now we have our constant in the numerator, and then we have 1 minus our common ratio. And I'll put parentheses around that whole thing. This whole expression is going to be our common ratio r. All right, so now this function is in the form of the sum of a geometric series, and so we can rewrite our function as a geometric power series. All right, so a is equal to negative 2, and r is equal to 1/2 times 3x minus 18. All right, so this will be equal to the sum from n equals 0 to infinity of a, which is negative 2, times r to the power of n. So we'll have 1/2 times 3x minus 18 to the power of n. Okay, and so what we actually have here is our power series that has 3x minus 18 within it. In fact, we can pull out that 3 from 3x and negative 18. And if we do that, we'll be left with x minus 6, right? That's what we wanted from the beginning. And so if we pull that 3 outside, we'll have 3/2 instead of 1/2. So we'll have 3/2, and then we'll be multiplying by x minus 6. All right, so we have x minus 6. And so now if I clean up my work, we can simplify this power series a little bit. I'm going to start by taking 3/2 and x minus 6 to the power of n. And so if I do that, this will be equal to the sum from n equals 0 to infinity of negative 2 times 3/2 to the power of n times x minus 6 to the power of n. All right, and so now we can take 3 to the power of n and 2 to the power of n. So I'll rewrite this again. We'll have the sum from n equals 0 to infinity of negative 2 times 3 to the power of n divided by 2 to the power of n times x minus 6 to the power of n. Now we can actually simplify this further. The reason why I took 3 to the power of n and 2 to the power of n is because 2 can be moved to the denominator if we make the exponent negative, right? So we'll change this from being negative 2 to being negative 1 divided by 2 to the power of negative 1, right? If we move 2 to the denominator, instead of being 2 to the first power, it'll be 2 to the power of negative 1. And now we can add the exponents for 2 here in the denominator, right? We have 2 to the power of negative 1 times 2 to the power of n. We have the same base, so we can add the exponents and have n minus 1. All right, so our final answer is that our power series will be equal to the sum from n equals 0 to infinity of negative 3n times x minus 6 to the power of n divided by 2 to the power of n minus 1. All right, and so that is the power series centered at 6 that represents this function. All we have to do now is find the interval of convergence. So if I clean up my work, to find the interval of convergence, remember, we just have to check to see when the absolute value of r is less than 1. In this case, r is equal to 1/2 times 3x minus 18, or we could also rewrite that to be 3/2 times x minus 6, right? We pull out that 3 to have x minus 6, and so we have 3/2 times that quantity. And so, when is the absolute value of 3/2 times x minus 6 less than 1? Well, this 3/2 is not going to be affected by the absolute value bars. It's already positive, so I can move that to the outside, and we'll have the absolute value of x minus 6 and 3/2 multiplied by it. And so, if we divide both sides by 3/2, or multiply both sides by 2/3, the reciprocal of that value, then we'll have the absolute value of x minus 6 is less than 2/3. And right here, we can determine the radius of convergence because we have the absolute value of x minus 6, the part that's raised to the power of n in our power series. And so since that's less than 2/3, we could say that the radius of convergence is equal to 2/3. All right, so if you wanted to make a note of that, you could. But what this statement is telling us is that x minus 6 is less than 2/3, but greater than negative 2/3. All right, that's what the absolute value of x minus 6 less than 2/3 is saying. And so now if we solve for x by adding 6 to each part of the inequality, remember that 6 would be the same as 18/3 because 18 divided by 3 is 6. So negative 2/3 plus 18/3 would be 16/3, and that will be less than x, which will be less than 2/3 plus 6, or plus 18/3, which will be 20/3. All right, and so what we learn is that when the values of x are between 16/3 and 20/3, our power series is a convergent series. This power series represents this function for the values of x between 16 thirds and 20 thirds. And so our interval of convergence is from 16 thirds to 20 thirds. Okay, and that is the final answer to this example. And so with that, let's look at one more example for this video. All right, so here's our last example. We want to find a power series for the function f of x is equal to 4 divided by x squared plus 2x minus 3, and we want that power series to be centered at c equals 0, and we want to determine the interval of convergence for that power series. All right, now this function here is a little bit different than what we've been working with so far. Instead of having a linear denominator, we have a denominator that is quadratic. More specifically, we have a quadratic with both an x squared term and a term with x to the first power. And here's why that's a problem. Since we're working with this function, where we have 4 divided by x squared plus 2x minus 3, it's not going to be very easy to get that in the form of a divided by 1 minus r. If we didn't have this 2x term, then we would be able to work with this as is, because then our common ratio r would just be working with a value of x squared. But in this case, since we have x squared and 2x and negative 3, that method's not going to work. Instead, what we're going to have to do here for a quadratic denominator like this is factor it and then split up the function into partial fractions. And so that's going to involve a lot of work, but what's going to result from that are two partial fractions that can then be manipulated into this form of a sum of a geometric series that we can then rewrite as power series. Okay, and so let's get started with that process because there's a lot of steps involved. First thing that we want to do is factor this denominator before we can split it up into partial fractions. So this will be equal to 4 divided by x squared plus 2x minus 3 factored. Now a quick trick for this is since the coefficient of x squared is just 1, we can ask ourselves this question: what two factors of the last term, negative 3, added together will give us the coefficient of the middle term? In this case, positive 3 and negative 1 multiplied together give us negative 3, and positive 3 minus 1 is positive 2. So our two factors will be x plus 3 and x minus 1, right? 3 times negative 1, negative 3, 3 plus negative 1, positive 2. Okay? And so our two partial fractions are going to be some constant a divided by the first linear factor of x plus 3, and that's going to be added to another partial fraction with a coefficient of b, and that will be divided by the other linear factor of x minus 1. Okay, so now we have to solve for a and b to figure out what these partial fractions will be, and the easiest way to do that is to take the numerator that they're equal to, which is 4, and set that equal to each of these coefficients multiplied by the factor that they don't have in the denominator. Right, we're splitting up this function into these two partial fractions, and it has a denominator of x plus 3 times x minus 1, but each of these fractions only has one of those factors. So we're going to set 4 equal to a, and that a is going to be multiplied by the factor it doesn't have in the denominator, which is x minus 1. So we'll have a times x minus 1, and we're going to add that to b times the factor that it doesn't have in its denominator, which would be x plus 3. So we're going to have x plus 3. Okay, essentially all we're doing here is getting a common denominator on both sides of this equation and then setting the numerators equal to each other, but I'm just using a little shortcut to get to this equation faster. If you want to see the whole process of partial fractions, be sure to check out my other video where I focus on partial fraction decomposition and how we use it to solve certain integrals. Okay, but anyway, let's work on solving for our values of a and b. And the way we're going to do that is by choosing convenient values of x. For example, if we let x equal 1, then we'll have 1 minus 1, which is 0, and so a times 0 is 0, and that will eliminate a from the equation and allow us to solve for b. So let's start with that. When x equals 1, we will have 4 is equal to 0 plus b times 1 plus 3, right? Like I just explained, when x is 1, we have a times 1 minus 1, which is a times 0. So that's where this 0 comes from. And then we have plus b times 1 plus 3 right here. Now 1 plus 3 is 4. So we will have 4 is equal to b times 4. And if we divide both sides by 4, we'll find that b is equal to 1. All right, now to solve for a, we can plug in negative 3 for x, and that will eliminate this term because negative 3 plus 3 is 0, and 0 times b is 0. So that will allow us to solve for a. All right, so when x equals negative 3, we will have 4 is equal to a times negative 3 minus 1 plus 0. Okay, so x is negative 3, so we have a times negative 3 minus 1 plus 0. All right, now negative 3 minus 1 is negative 4. So we have 4 is equal to a times negative 4. And if we divide both sides by negative 4, we will find that a is equal to negative 1. All right, and so now we can replace each of those coefficients with the values that we found. So a is equal to negative 1. So I'm going to rewrite this to be negative 1. And we found that b was equal to positive 1. So I'll rewrite that b to be positive 1. Okay, and so now we're done with the partial fractions work. We have successfully decomposed our function into two partial fractions. And so now notice that both of these fractions can be easily manipulated into the form of a divided by 1 minus r, the sum of a geometric series. All right, so what we're going to have to do is represent each of these partial fractions as a power series and then combine them at the end. So we're going to have to work on each of these individually. So if I clean up my work, let's start by working on this partial fraction. If we want this to be in the form of a divided by 1 minus r, and remember that the power series that we're writing here will be centered at 0, so we're just looking for that r to include x. We don't have to add or subtract any constants to that. And so what I'm going to do first is rewrite that to be negative 1 divided by 3 plus x. I just changed the order of these terms in the denominator, and so now x is in the position where r, the common ratio, should be, but we need that common ratio to be subtracted from 1, which we'll work on getting 1 later, but we want this to be minus some common ratio, and so let's rewrite this plus sign to be negative by making x negative. Right, so what I mean by that is we can say that this is equal to negative 1 divided by 3 minus negative x. Right, two negatives make a positive, so 3 plus x would be the same as 3 minus negative x. And so negative x is going to be our common ratio r, and now all we have left to do to rewrite this partial fraction into this form is to change this 3 to be a 1, right? We want to have 1 minus the common ratio. And so we can do that by multiplying by a form of 1 divided by 3, or 1/3. Essentially, we are dividing the numerator and denominator by 3 so that this 3 will become a 1. All right, so if we do that, we will have negative 1/3 divided by 1 minus negative x divided by 3. Okay, 1/3 times negative 1 is negative 1/3. 1/3 times 3 is positive 1, and 1/3 times the negative x is negative x divided by 3. And so now our partial fraction is in the form of the sum of a geometric series. In this case, a is equal to negative 1/3, and r is equal to negative x divided by 3. And so we can rewrite this to be the sum from n equals 0 to infinity of a, which is negative 1/3, times r to the power of n, which will be negative x divided by 3 to the power of n. Okay, so now we have a power series for our first partial fraction, and we'll come back to simplifying this later. For now, let's now work on the second partial fraction. So if I clean up my work, remember that these were the values of a and r for this partial fraction, or this power series. But now we're going to work on the second partial fraction, which will make another power series. And so once again, the first step I'm going to take is to reorder the denominator. So we're going to have that this is equal to 1 divided by negative 1 plus x. And by doing that, this x is now in the position to be the common ratio r. But we do want to subtract that common ratio. So we want to have negative 1 minus some common ratio. And so we'll do what we did for the other fraction. We will change this plus sign to be negative by making x negative, right? So this will be equal to 1 divided by negative 1 minus negative x. If we subtract negative x, that's the same as adding x. And so our common ratio is going to involve negative x. Now all we have to do to get this in this form is to make this negative 1 positive 1. So in this case, we can multiply by a form of 1 of negative 1 divided by negative 1. And that will make this negative 1 positive 1 so that this is in the correct form. So if we do that, negative 1 times 1 is negative 1. So this will be equal to negative 1 divided by negative 1 times negative 1, which is positive 1, minus negative 1 times negative x, which is positive x. And so we just have 1 minus x in the denominator. Okay, and so now this fraction is in the form of the sum of a geometric series, and so we can rewrite it as a geometric power series. In this case, a is equal to negative 1, and r is equal to x. All right, so if we rewrite it as a power series, we will have that this is equal to the sum from n equals 0 to infinity of a, which is negative 1, times r to the power of n. So we'll have x to the power of n. All right, and so now we have rewritten this second partial fraction as a power series, and so we can add that power series to this power series. All right, so we'll have plus the sum from n equals 0 to infinity of negative x to the power of n. Okay, and so now what we want to do is simplify these two power series and combine them into one power series that will represent this entire function. Okay, remember that these two partial fractions are equal to this function. I know we did that a little while ago now, but once we combine these power series into one power series, that power series will represent this function. And so let's start by simplifying this power series. We can rewrite negative x divided by 3 to be negative 1 times x divided by 3, right? So this will be equal to the sum from n equals 0 to infinity of negative 1/3 times negative 1 times x divided by 3 to the power of n. And then to simplify this a little bit, let's pull this negative to the outside. So we are subtracting this sum from n equals 0 to infinity of x to the power of n. All right, now in this power series, we can take each part of this quantity to the power of n. So we'll have negative 1 to the power of n, x to the power of n, and 3 to the power of n. And so I'm just going to do that right here. I'm going to erase those parentheses and have negative 1 to the power of n, x to the power of n, and 3 to the power of n. All right, and so now notice that both of these power series are sums from n equals 0 to infinity. And so we can combine their contents. And so if I clean up my work, what we can now have is that this is equal to the sum from n equals 0 to infinity of negative 1 to the power of n divided by 3 times x to the power of n divided by 3 to the power of n minus x to the power of n. All right, all of this is part of this series. And now we can simplify a little further. We have 3 and 3 to the power of n in the denominator, so we can combine those exponents and have 3 to the power of n plus 1. And then also notice that we have x to the power of n in both of these terms, and so we can pull out x to the power of n from each of those terms. So what we'll have is the sum from n equals 0 to infinity of x to the power of n times negative 1 to the power of n divided by 3 to the power of n plus 1 minus 1. All right, so we pulled x to the power of n out of each term, so that's no longer in the numerator of this term, and then we just have minus 1 for that last term. Okay, now one more thing that we can do to finalize the simplification of this power series is notice that this negative out front could be combined with this negative 1 to the power of n, right? This negative, we could rewrite that to just be negative 1 times that fraction. And so negative 1 times negative 1 to the power of n, we could combine their exponents, right? We have negative 1 to the first power and negative 1 to the power of n. So we could add the exponents and have negative 1 to the power of n plus 1. So what I'm going to do is just erase this negative 1 out front, and what we'll have instead is negative 1 to the power of n plus 1. Okay? And so this right here is the power series centered at 0 that represents this function. We have the sum from n equals 0 to infinity of x to the power of n times negative 1 to the power of n plus 1 divided by 3 to the power of n plus 1 minus 1. Okay, and so now all that's left to do is determine the interval of convergence for this power series. All right, now that's actually going to be a little bit more difficult than it was in the past because this power series is a combination of two power series, one that came from each of these partial fractions. So that's why I saved these values of r for each fraction, because what we're going to have to do is look at the interval of convergence for each power series, and then the intersection of those intervals will be the interval of convergence for the combined power series. All right, so let me show you what I mean. If I clean up my work, if we start by looking at the interval of convergence for the power series that resulted from this partial fraction, we're going to be looking at the absolute value of r, which is negative x divided by 3, and that needs to be less than 1 in order for the power series to converge. And so the absolute value of negative x divided by 3 will be x divided by 3. And so we can ignore that negative sign, and then this 3 is not going to be affected by the absolute value bars. So we can rewrite this to be 1/3 times the absolute value of x, and that will be less than 1. All right, so the absolute value bars remove that negative, and then this 1/3 is always positive, so we'll just pull that out. And now we can multiply both sides by 3 and find that the absolute value of x will be less than 3. And what that will tell us is that x will be less than 3, but greater than negative 3. And so when x is between negative 3 and positive 3, the power series for that first partial fraction would be a convergent series. All right, so the first interval of convergence is from negative 3 to positive 3. And so now we want to compare that to the interval of convergence for the power series of the second partial fraction, and then the intersection of those two intervals will be the interval of convergence for this combined power series. Okay, so if I clean up my work again, this was the interval of convergence for the power series that resulted from this partial fraction. And now let's find the interval of convergence for the power series from this partial fraction. In this case, r was equal to x. So we're going to be looking at the absolute value of r, or the absolute value of x, and see what makes that less than 1. But this is pretty simple. The absolute value of x less than 1 implies that x needs to be less than 1 and greater than negative 1. All right, so that interval of convergence is from negative 1 to positive 1, which means that the power series that resulted from this partial fraction converged when x was between negative 1 and positive 1. All right, now we have both of our intervals of convergence. And so what is the intersection of these two intervals? What values of x do they both include? Well, this interval is smaller than this interval, right? This one contains values from negative 3 to 3, but this one only contains values from negative 1 to 1, and all of these values could also be found within this interval. Negative 1 to 1 would be the intersection between these two intervals. All of the values of x from negative 1 to 1 would make the power series for this partial fraction convergent, and those values of x are contained in this interval of convergence, which would also make the power series for this partial fraction convergent. So negative 1 to 1 is going to be our combined interval of convergence for this power series. All right, so our final answer is that the interval of convergence for the power series that represents this function is the values of x from negative 1 to 1. Okay, we're not going to include any of those other values from 1 to 3 or negative 1 to negative 3 because those values of x would result in a divergent power series for this partial fraction. All right, so since we combine those power series into one, we need that intersection of those intervals of convergence. Okay, and so that was it for this last example. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.